keep an eye on participants coming in, because I know a couple of people are joining. And so I always give credit when I'm talking in the Midlands. Oh, somebody's having trouble getting in. Okay. I always give credit to a man that I'm sure a lot of you are familiar with. This is Professor John Feehan, who not only taught me an awful lot about geology of the Midlands and of the west coast of Ireland, but also reignited my love and my passion for geology as I had become an archaeologist. And some of the things he said to me that I'd learned during my degree suddenly made sense. Anyone who's had the joy of working with him, be it on geology or flora or fauna, will know how unbelievably easy he makes everything for everyone. So this little circle shows geological time from the beginning of our planet, 4,600 million years ago, to the current day. So starting at 12 o'clock, ending at 12 o'clock. And really, I'm only putting it in to give you a sense of the vastness of human time. Because when you talk about 4,600 million years ago, it's hard to get your head around the concept of that time. But let's just say that very little happens, and that's really, really unfair to the time, up till about now, up till about here, which is about 450 million years ago, and the Cambrian period. So, which is what we call the Cambrian life explosion. And life as we know it and as we see it in terms of creepy crawlies and organisms, that's when we see that explosion of life. About 250 million years ago, in the Mesozoic starts, and that's the rise of the dinosaurs. And they last to about 66 million years. So this green bit here is our Jurassic Park. This is our rise and fall of the dinosaurs. When you look at it in the context of time on our planet, I mean, it's after 11 o'clock if you think about this as a clock. And then from 65 million years or so, we see what we call the rise of the mammals. And the black line from about 2 million years ago is the first hominins, Lucy and the like, and us. So you can see how insignificant we are. It is unfair to consider us, we really are part of this mammalia group. So, but we're still very young and very short on this planet, not that you tell by the impact we've had on it. Geology is really important to humankind because we use stones to make things. From the Neolithic farmers who needed stone tools to chop down forests, the great stones at Newgrange that were imported from vast distances to make these incredible monuments. In medieval times, stone was still used imported stone was still used. So, sorry, my screen there. To the lifetime, or the tracing the life of buildings. So that's me standing on against a tower in County Wexford. That was a tower built to look like an early Christian round tower that's actually a Crimean War monument. But that tower was made out of the last of an Anglo-Norman castle. And by looking at the stones, I was able to say, okay, well, this is where they got the stone to build the castle. This is what happened to it. And it didn't just end up here. It was used in a bridge nearby, and it was used in a Protestant ascendancy house nearby as well. So geology is very useful for those things. But it's not just in terms of sourcing stone. Geology is what forms our landscapes, from our U-shaped valleys, our rivers, our mountain tops, our plains, our bogs, that even the Burren landscape. Geology, I suppose it's a twofold process. The bedrocks in geology control how humans inhabit an area. So if you understand the geology, you'll understand where you're going to find people, where you're going to find evidence of people. And also humans' impact on the geology, they impact on the landscape. And that interrelationship is really important in understanding human habitation and human settlement. So I'm going to show you a short video. It's a couple of minutes long, and I'm sure you're familiar with the concept of plate tectonics, that we're not on a fixed planet, that our continents, we're sitting on the western extent of the Eurasian plate, There are a whole series of plates around the planet. I'll show you them in a minute, but that these move, and they move because underneath the crust, if you go down into the earth, there is a liquid mantle. And this is molten rock that has convection currents in it that are causing the plates to move around. And this video is a predictive model of what's going to happen to our planet over the next 250 million years. I'm showing it to you for two reasons. First of all, to get your head around the fact that for entire human existence, the planet and our plates have looked more or less like they look today. But if you consider that that's only a moment in time, in geological time, that we are constantly moving. I think somebody's accidentally drawn on my screen. I love that video, especially because what it's predicting is more or less a rewinding of the planet, of what's happened over the last 400 or 500 million years from one supercontinent. And you can see as these plates move around and as they interact, that's how geology is formed. That's how rocks are formed. Sorry. So these are the current plates. There's us sitting on the Eurasian plate, and we're moving eastwards. The North American plate is moving westwards, maybe not a bad thing. And in the middle of that, because the crust is thinning, because they're moving apart and the crust is thin, that results in volcanic activity. And so that's why Iceland has volcanoes on it, because it's sitting on this trench where the trenches are pulling apart, and it allows magma to come up from the mantle and form these volcanoes. And then you can see the African plate is moving eastwards, and resulting the Himalayas, or the Alps are still rising. The Himalayas are still rising as the Indian subplate is moving northwards. So all of these processes, you've got the San Andreas Fault resulting in as a result of the Pacific going underneath the North American and South American plates. This constantly moving, constantly changing planet. Geology is a relatively old study. There's geological maps of pretty much the entire planet now. And the handy thing about it is there's a worldwide agreed convention on the naming of different time zones. and different processes. And of course, they're incredibly complicated, but there are simplified versions of them as well. So we've identified different timing units throughout time. Now, this is the same drawing as the circle I just showed you, or it's showing the same information, but the really large part of it is squished down to the bottom from 4,600 all the way up to 540, squished down to the bottom. So we have from the Cambrian up, and there's three major units: the Paleozoic, the Mesozoic, the Cenozoic, and then each of those are divided up. So as I said, that's the period of the dinosaurs. And the dinosaur extinction event that happened at the end of the Cretaceous is only one of 5 major extinction events where vast quantities or vast percentages of the species on the planet have come a cropper and have become extinct. And it's not the last. We're in the, many believe that we're in a mass extinction event at the moment. So for the next 25 minutes or so, 20 minutes, I'm going to give you a whistle-stop tour of the geology of Ireland. I'm going to focus in on the Midlands, but it doesn't make sense to just talk about the Midlands. You have to look at the whole of the country. And Ireland's geological history is far more complicated even than its political history or its archaeological or its history, its human history. It's a remarkable little snapshot into the world's geological history. I love this map because not only does it show geology, each different geological rock type is represented by a different color. It also shows topography. It shows the elevation. So you can see the mountains. There's the Wicklow Mountains. There's the Donegal Mountains. There's the Oxbows, the Killarney Mountains. And Ireland is often described as having a bowl shape. So we have the generally low-lying Midlands of Ireland, everything pretty much under about 150 meters, surrounded by, on the west, south, and southeast and northwest side, by much older rocks that form mountain chains. And then in the northeast are also mountainous, but in the northeast are, as we'll find out shortly, that they're younger rocks. And the middle is the Carboniferous limestones. So it gives this sort of sense that there's this sort of flat Midland surrounded by upland areas. There's another thing you might notice from this map, and you'll see it when I bring up, that's the simplified, just the colors, that there are a number of trends. You can see, hopefully, that there are trends going from the northeast to the southwest. And you can see them here in what's known as the Longford Down Massif. You can see them in the northwest foreland of Donegal. You can see them in County Sligo, and you can see them here in the southeast of Ireland, in County Wicklow and County Wexford and into Waterford. But there's these patterns, and they're there for a reason. They tell us something. So I'm going to go all the way up to the northern tip of the country to talk about the oldest rocks that we have in Ireland. So remember, the planet's been around for 4,600 million years, but the oldest rocks in Ireland occur in parts of Donegal, Sligo and Mayo. And I'm just bringing you up to a little island off the coast of Donegal. And the rocks that these people are standing on are actually the deposits of a glacier. So during an ice age that happened 1,700 million years ago, sediments were deposited by this glacier, and they survive here up in the northern part of the country. Now, they were two things. First of all, they were glacial deposits, but since then they have been through an awful lot. 1,700 years of geological time means that you're going to be lifted up into mountains, you're going to be squashed, you're going to be crushed. So they don't look like glacial deposits, as I'll show you later what glacial deposits look like. They've been heated and squished and bent into shape. The other thing is, and this is where geology can often melt your head, is if they're glacial deposits, it means that a glacier picked up sediments from somewhere and deposited them here. That means those sediments already existed. So all of the stones, all of the rocks that we see in this planet originated 4,600 million years ago and are just being recycled. To show you what the planet looks like at the time, the Geological Survey of Ireland have a series of reconstruction drawings of what the planet looked like based on geological evidence over time. And this is going way back to when these rocks were formed. So they show you the land masses, and essentially there's Gondwana and Laurentia, two major land masses. And also they show the outlines of and some names of places that we, as they are now. So there's India there on the equator, there's Australia. So everything's in a different place. There's Antarctica on the equator, there's Africa, there's Laurentia is mostly made up of North America. But what you'll probably notice are two things about Ireland. One is that we're on the South Pole, which of course makes sense because that's where the glacial deposits came from. But secondly, the southeast of Ireland and northwest of Ireland are separated by vast distances, huge distance, thousands and thousands of kilometers. So we haven't even formed as one distinct landmass yet. There's a big gap in the geological record then. The next oldest rock we have in Ireland are probably about 800 or 900 million years old, and they occur in the Oxbow Mountains here. And then the next oldest are in here around the Bray Head area. But we do know an awful lot about these sediments, and the reason we know about them is because they've been uplifted from where they were originally deposited. So we're going to go on a little journey to talk about rocks that occur in this area here, in the Longford Down Massif, and then later we'll talk about the Oxbow Mountains here. Handily enough for us, these rocks are preserved on the Laois Offaly border, and this is John Fian's book of the geology of Laois and Offaly and the map, geological map of it. And people tend to think of the Midlands of Ireland and Laois and Offaly as being limestone. But of course you have the Slieve Blue Mountains. And the Slieve Blue Mountains are a little sliver of information about what was happening before the Carboniferous period. Now, there's a vast amount of time happening here. So you can see you're talking about 1,000 million years have passed between the last image I showed you and this image here. Amanda, if you could do me a favor and let Elizabeth Dunn in, please, there. There's Gondwana land. So Gondwana land, if you remember, was based around here, and Laurentia was actually based here. So they've done a little merry dance and they've flipped around. And the northwest of Ireland is still attached to Laurentia, which is essentially North America. And the southeast of Ireland is attached to Africa and what will become Europe. They're separated by a vast ocean. And that ocean is called the Iapetus Ocean. The Iapetus in Greek mythology is the father of Atlas. So the Iapetus Ocean being the father of the Atlantic Ocean. There is no Atlantic Ocean. They call this the Panthelastic Ocean, which essentially is this major ocean that's always existed and is now the Pacific Ocean. But what we've got to think about is what's going to become Ireland, because what happened next was a chunk of Gondwana land broke off and started to drift northwards. And that's what's eventually going to become Ireland. So the landmass that is going to become Ireland isn't actually there or there, it's actually in the ocean, where vast quantities of sediments form. So if anybody has seen a Jacques Cousteau or seen a David Attenborough documentary and they're in a submersible and the lights are shining out in the deep ocean and you see all these amazing creatures swimming around, also in the background you'll see dust. You'll just see that there's this constant dust settling at the bottom of the ocean. And that dust is made up of sediments that have been blown across the ocean from deserts and from beaches and blown, and have just settled on the Earth's top of the Earth's surface. It's moon dust, stardust, just settling down from the atmosphere, landing on the top of the ocean and then settling down. And it's also, of course, animal feces and decaying and dead animals, like skeletal remains of animals. And they all make their way to the bottom of the ocean. And anybody who hasn't vacuumed their house for a week or so will know that that dust gathers. And it may gather as a tiny little layer, but over geological time, that forms kilometers thickness of material. So what is to become Ireland is now being deposited at the bottom of this ocean. And as a chunk of Gondwana land breaks off and starts to move northwards, that material starts to get crushed. And when two continents move together, all of that material has to go somewhere. So some of it will get subducted. That means will be pushed under. If you have two land masses that come together, or if you have an ocean that is pushed against a continent, it will go dip underneath it, just like is happening today on the western seaboard of the United States, where the Pacific plate has subducted, has gone underneath the North American continent. So that's what's happening here, and it's what's happening here as this ocean starts to close. And this is a little diagram of what happens during that process. So out in the deep sea, we've got all the sediments that I talk about, or forming layer upon layer of sediments out at sea. But at the land, you have land, and this is land now at the same land as we have now. You have land that you come down to the shore, and it goes to what's known as the shelf, and then eventually dips out into the deep sea. So if you go out off the west coast of Ireland and you're extremely tall, you can walk out and you'll get deeper and deeper, but the slope is quite shallow, and eventually it dips into the deep sea. That interface is really, really important. And it's really important because sediments settle on that slope, and they sit there on that slope, and they're what we call metastable. They're not going to go anywhere. They're on a slope, but they're not going anywhere. But because those land masses are pushing together, every now and then the pressure builds up and there's an earthquake. And every time there's an earthquake, all of that material gets shaken and it starts to flow downstream. So it's like a landslide, but because it's happening underwater, all of this material gets mixed up with water, and it forms what we call a turbidity current that swishes down into the deep ocean. So it flows down into the deep ocean and settles in the ocean. So every time there's an earthquake, all this material that's settled on the slope flushes down into the ocean and settles. And it settles down over time, like our pint of Guinness. You know, when you pour a pint of Guinness, you see all the clouds. And if you got a jar, a good thing to do with kids. If you get a jar or a pint glass and you fill it with water and get some coarse grained sand and then some finer grained sand and then some mud and some chalk, and you shake it all up and leave it to settle, the coarser grain, the bigger grain settle at the bottom, and then on top, and as you go upwards and at the very top, you get the finest sediment. So it's a graded settlement, because that's how nature works. That's how the gravity works on these things. And this is the result. So each one of these, so that from there to there, that is what's known as a turbidite, or and basically what that represents is all of the material. So there was an earthquake and that material flowed down into the deep ocean and settled. And this is the coarser grain material, and then it gets finer all the way to the top. So what we're looking at here is an earthquake that happened maybe 450 million years ago. And that's the deposits of it. And there's one earthquake, there's another earthquake, there's another earthquake. And this is what we see in the Sleeve Bloom Mountains today. So you see them in the Sleeve Blooms, you see them in the southeast of Ireland, you see them in the Longford Down Massif, and they're called grey wackies because they're grey and they're wacky. That's simple. And interestingly, in Newgrange, there are 547 huge stones between a ton and 10 tons in size that were used to make the perimeter and the main structures inside the passage. Some 3,200 BC, so over 5,200 years ago. They were made out of grey wacky sandstones that they brought from Clogherhead down the river and up the River Boyne Valley. So somebody thought this rock wasn't just grey and wacky, they really liked this rock. So that entrance stone that I showed you is made of grey wacky sandstone. So this process is preserved here, little snippet of it in the Sleeve Bloom Mountains. But on the up in the northwest of Ireland, it's also seen in the Oxbow Mountains. And the Oxbow Mountains are actually older. They're mostly comprised of the deep sediments that were underneath the ocean. So why have they come to the surface? Why can we see them? If these were deposited in a deep ocean, why can we see them? So there's the Oxbow Mountains today. They're quite low-lying mountains. So let's just take a look in here. So this is the part of Ireland that broke off Gondwanaland. You can see Gondwanaland still moving up this side, but this breaks off Gondwanaland and it starts to move this way. So we have a major fault where the Appalachian Ocean is going underneath the Laurentian plate and the Avallonian plate as well. So we have all of this activity and all of this material forming in this ocean. Eventually what happens is that ocean closes. So they come together and the Appalachian Ocean closes there. So all of that material that was at the bottom of the ocean gets pushed together, and it has two choices. It goes down or it goes up. When it goes down, it gets melted and it comes up as volcanoes, or as what we call granite plutons, these huge granite plutons like the Leinster Mountains. But if it goes up, it forms these huge mountain chains. And because this came from this direction and that came from that direction, so Laurentius come from the northwest, the Avallonian subplate has come from the southeast, all of the pressure is coming that direction. What happens is the mountains line up northeast to southwest because they're trying to fill up the least space. If you squash everything together, they'll take up the least amount of space. Down to the microscopic level, if you look at the minerals in these rocks, they're so desperate to not get squashed that all the minerals lined up facing northeast to southwest, and you get these mountain chains forming. And you might remember when I showed you the geological map of Ireland, a lot of the rocks are oriented that way. And that's because of what happened, this huge, it's called the Caledonian mountain building event. It squashed together. So that red line is the Iapetus suture. This green blob and that blue blob are trilobites, and they're fossils of organisms that lived in the sea, that swam around in the sea for tens of millions of years. And the funny C-shaped things are graptolites. So there's green ones and there's blue ones. And geologists noticed that you can get in rocks that are 400 and 500 million years old in Ireland, you get trilobites and you get graptolites throughout the country in rocks of this age. But they noticed that there was a difference between the ones in the south east of Ireland to the ones in the northwest of Ireland. And probably a good analogy is if you imagine a species of cod that are coastal species. I don't know much about cod. I know they're a deep water fish, so I shouldn't have said cod, but I'm going to stick with it. Imagine a species of cod that live all of its life on the off the shores of Nova Scotia in Canada. So in the western extent of the Atlantic Ocean. And the similar cod are swimming off the coast of west of Ireland. And they do that for millions of years. They will evolve differently. If they don't interact with each other, they'll evolve differently. They'll still both be cod, but they won't look like each other. They'll evolve differently. If the Atlantic Ocean closes and we come together with North America, in the geological record, you're going to have cod that on one side are one species, and the other side are another species, even though they're geographically very close to each other. So these grew up on one side of and evolved on one side of the Iapetus Ocean. These evolved on another side of the Iapetus Ocean. And it isn't just in Ireland. If you go into the south of England, you get the same species of trilobites and graptolites that you get in the southeast of Ireland, the same in Scandinavia. If you go northwest of the Iapetus suture, you get a different species of trilobites and graptolites, but they're related to the ones in Greenland and Scandinavia. So just to put that in geological terms, there's the Oxbow Mountains. If you extend to the northeast, that mountain chain extends into the northwest foreland of Scotland, up into Scandinavia, and if you go to the west, it extends into the Appalachian Mountain Trail. So that's the Appalachian Mountain Trail. So when I talked about the Iapetus Ocean closing and this huge mountain chain forming, that mountain chain runs all the way through the Appalachians into Ireland, into Scotland, and into Scandinavia, the same mountain chain. And I've hiked in both and they look exactly the same. If you do me a favor and there's somebody else has arrived in there, Amanda, if you could let them in, please. I think the problem with my screen occurs when I move off my screen to try and let someone in. Thanks a million. Okay, so that's a pretty amazing concept. You've got this sort of merry dance for 1,000 million years of our continents, and the parts of Ireland have come together and formed this huge mountain chain that you can see in the rock. So you can see it here, you can see it there, and you can see it there. That alignment of those rocks is as a result of that mountain chain. What happens to mountain chains? They get eroded away. And we see that particularly in the southwest of Ireland, in County Kerry and in County Cork. And they're coloured sort of browny colours here, and it's known as the Old Red Sandstone. And luckily again for Laois Offaly is that we see them preserved in the Slieve Bloom Mountains, beautifully preserved. So there's a reminder of where we were. We built this mountain chain, so that went all the way down here into Laurentia, all the way up here, this mountain chain. It now starts to get eroded away because that mountain chain is exposed to the elements, and river networks form and rain falls on them, and the material starts to get eroded away. Where? Back into the Iapetus Ocean to the south. And it forms these huge rivers that flow through the mountains and deposit huge amounts of material. Vast rivers. If you think about an aerial photograph of the Gulf of the Gulf and the Mississippi flowing into the Gulf, it's this fan of material that's coming from the upland areas. And this is actually a picture of it. I'll show you a picture from the Slieve Blooms shortly, but this is a picture because it's a very nice example of it in Dunmore East in the southeast. And you can see these beautiful red sediments here. The handy thing about these is there are modern rivers and we can compare them. In fact, all geological processes can be compared to modern examples because the processes are still happening. So think about a river. You've got a river flowing through a landscape here. In the bends of the river, next time you're standing at a river, have a look at it. At the bends of the river, at the outer bend, the water is actually flowing really, really fast. So what it does is it washes off the fine sediment and leaves the coarser grained, the bigger stones get rounded and get pushed to the sides. And that's what they look like. So it looks like a beach deposit. If you stand in a river today, a fast flowing river, you look at the outer bend of it, it'll have all these cobbles that have been rounded, all the sediment's been pushed away. And that's there in the big rock, in this sediment here, you can see a unit of it. In the middle of the river, the flow is more consistent, it's fast, but it's not super fast, and you get all the gravels being deposited. And that's this red there, sort of gritty material, that's the riverbed. Every now and then a river will flood, and when a river floods, the water levels rise and they span across the floodplain, and then as they recede again, a layer of mud is deposited. And in here, it might be hard to see, but you can see there's a slightly different, a more browny red, and that's the finer grain material. And of course, this can be a little bit confusing because we're looking here at time. So the oldest rocks are at the bottom, the youngest rocks are at the top. And how come we have a river and then we have a floodplain and then we have a river and then we have a bend in a river and then we have a river again, a riverbed again in the same place? Well, the reason is rivers change their course. So if you think about this river here, if this river flooded, when the flood subsides, the course of the river may have changed. So what was a bend in the river may become the floodplain, and what was the middle of the riverbed could become a bend, etc. It's also important to know that this time period is called the Devonian period, and it's known as the time of the fishes, because there were something like 300 times the amount of species recorded from the Devonian period than we have of fishes today. So the seas were swimming with fishes, but in Ireland, our deposition is rivers, so we don't get this incredible fossil record. Here's the Slieve Blooms, and there's two pictures. The left picture is from the Glenbarrow River, and I love this because these are the sediments that were laid down by that huge river network into at the edge of the Iapetus Ocean. So if you think about these rocks that these people are standing on, and what happened to them. So what we know is they were originally deposited at the bottom of the Iapetus Ocean. They were then pushed upwards into this huge mountain chain when the Iapetus Ocean closed. And then they were eroded away and deposited back into the Iapetus Ocean. And now, 400 million years later, they're being worn away by another river, by the Glenbarrow River. So it's really ironic for these poor rocks, what they've been through. These photographs will hurt your head. This is my favorite place. This is in the Silver Barrow River. It's my favorite place in the Sleep Blooms. You have to hike to find it, and you have to get a little bit wet. But my right foot is standing on the Greywacke sediments where my screen had got frozen. The sediments that were a result of the earthquakes depositing material at the bottom of the Iapetus Ocean. So those rocks underneath my right foot were deposited some 450 million years ago as the Iapetus Ocean closed and as earthquakes formed. They got pushed up into a mountain chain that had a whole series of rivers flowing through it. And those rivers brought with them sediments. It carried sediments from higher up and deposited them down in the river. My left foot is on top of those rocks, and they're the Devonian sandstones. Between my left foot and my right foot is 75 million years of time. And that's been shown here. There's the sediments on top. That's the river sediments on top of the older Greywackes that the river carved its way through. So after the Devonian, we have the time period that dominates our Midlands geology, and it's the Carboniferous period. By this stage, things have changed dramatically again. So we're into about 325 million years ago, and to this time when the continents have come together. Gondwana and Laurasia have come together to form the supercontinent Pangaea. And Ireland is on the equator. So if you think about it, we started in two places on the South Pole. We did this merry dance around the South Pole, came together and have been drifting northwards ever since. And as we drift northwards, different things happen. So we're not exposed at the surface, even though it looks like we're landmassed here. We're under a shallow tropical sea. A sea that's teeming with life, with incredible life. So you've got ammonites, you've got trilobites are still around. I think there's a trilobite swimming around there somewhere. There's a trilobite swimming around. You have lots of fish, you've bentonites, you've solitary corals, you've coral reefs, you've got these amazing things called crinoids, which are called sea lilies, but they're actually filter feeders. They're animals that attach themselves to the substrate. Absolutely teeming with life. And in Irish Carboniferous limestones, this life is there to be seen. The fossil record is remarkable. So Trim Castle's made out of limestone. An awful lot of our medieval buildings, both earlier and after and during the time of the Anglo-Norman arrival in Ireland, are made of limestone. Certainly it's the favorite building material in the Midlands of Ireland. And it's because of the way limestone forms. So it forms these layers that settle at the bottom. And in Ireland, they're gently folded. So they're not quite flat. They bend up and down, and they bend up and down because of another geological event that didn't happen in Ireland, but happened to the east of us. Are you okay, Amanda?
You were still on train. Yep.
Yeah. Okay, grand.
Yep.
And my voice is okay. You can hear me okay, yeah?
Yeah. It's slightly connected. Possibly if you say next slide, you know that we're with you. That's okay.
Okay.
Thank you.
Yeah. And your voice is echoey to me, Amanda. I'm not sure why, but
I'll try not to speak too much.
Okay, that's right. No, you need to stop me if it's going wrong, because I can't tell. So you're very good. So there was a mountain building event that happened way to the east of us, but unlike the Caledonian that resulted in those huge mountains like the Oxbow Mountains and the Longford Down Mountains, we were only mildly affected. So rather than pushing these limestones that were laid down in flat layers, they brought them to the surface and they just bent them slowly. They just bent them a little bit. They just formed these lovely gentle folds. And if you're driving along the M4 or the M6 and you drive through one of those road cuts, sometimes you look across, if you look across, now not if you're driving, if you're not driving, look across to those road cuts and you'll see these beautiful gentle folds. And those folds are aligned north-south. because this happened to the east of us. It pushed us slightly. So if you've been to the Hill of Tara, it's this beautiful north-south running ridge. The mountains to the east of it are the hills to the east of it are the Screen Hills, also forming a north-south running ridge. And that's because the rocks have been gently folded. And as a result of being gently folded, they're cracked. So they're the perfect building material. It forms in these lovely block-size units that you can extract and build buildings with. And so this is the moat of Trim Castle, and you can see the moat has actually been dug into bedrock, which has served two purposes. First of all, it gave you a moat that was into bedrock, which meant it was very difficult to, or impossible, to undermine the castle by digging underneath it. But also the excavation of that moat resulted in the building materials for the castle. This is a relatively common occurrence. So the rest of Ireland's geological history is a tale that's mostly in the northeast of the country. I'm just going to very briefly go through it. Ireland is continuing that journey northwards on the planet. It's come through the equator at the time of the Carboniferous, but as it drifts northward, the next rocks that we see represented in Ireland are actually around the tropics, and we're in around the same latitude as the Sahara Desert is now, and that's what we are. We're a desert. Beautiful red sandstone deserts. And these are preserved up in the north coast of Ireland. And this may look a little bit like the old red sandstone that we talked about in the Sleep Blue Mountains. It's red, and it's called the new red sandstone, imaginatively enough. But if you look closely at it, you'll see under the microscope, you can see that all the grains are sharp and angular because they've been eroded by wind as opposed to by water, which rolls everything. We continue moving northwards and into the Cretaceous period. At the time of the dinosaurs, we don't have a huge dinosaur fauna in Ireland, unfortunately, but we have these beautiful white cliffs along the Antrim coast, which are the same as the White Cliffs of Dover. They're the same rock formation. They're pure calcium carbonate made virtually entirely of the remains of organisms. And what's really important about them is in them, there's flint nodules, pure silica nodules that we're not really sure whether they are the result of sponges with a siliceous skeleton or how they form, but we get these incredible lenses and lozenges of flint that is essentially gold dust to the hunter-gatherer societies and Neolithic societies, because out of flint you can light fires, but you can also make sharp tools. Okay, we've taken quite a big step forward, but this is starting to look like the planet looks today, and the Atlantic Ocean is open. And it's amazing to think that for most of the geological history of our planet, the Atlantic Ocean didn't exist. And it's how we view the planet from an Irish perspective, how we look at the planet. From a European or an African perspective, you just see the Atlantic Ocean on our western side. But that ocean only began to open maybe 100 million years ago, and it opened later in the North Atlantic, and Ireland was at the very epicenter of that. So as the plates pulled apart, the crust thinned, and magma from the mantle came up, and that's what formed the Giant's Causeway. And this is what it would have looked like back 66, 70 million years ago, just like Iceland looks today. Eventually, Ireland drifted to the east of the mid-Atlantic trench, and the volcanic activity stopped, but it's beautifully preserved in the Giant's Causeway. So that's a whistle-stop tour of the geology of Ireland. But it's only part of the story, because if you look across the landscape, we don't have bare rock, or we don't have forests and trees growing on soil on top of rock. We actually have really, really big thicknesses of sediment on top of the rocks. And that's because of where we are located. We're at 54 degrees north. People often think we're across from New York or from Boston, but actually we're across from Nova Scotia or from Newfoundland. We're much further north than people think, and our climate is relatively benign because of the Gulf Stream. But for the last 2.5 million years, there's been a whole series of ice ages that have occurred when the planet cooled and the ice sheets in Antarctica and in the Arctic started to grow as they sucked seawater into them. The result of us being so far north is every time there's been an ice age, and there have been numerous, maybe every 120,000 years for the last 2.5 million years, Ireland has been completely inundated with ice. The last of those ice sheets retreated from Ireland some 12,500 years ago. And we're not talking snow, we're talking proper glaciers, 1 kilometre, 2 kilometres thickness in places of ice that would have covered all but the highest peaks in Ireland. And they've done more to shape our landscape than anything that's come before. Now, the bedrock underlying has had an impact on how the ice sheets moved across the landscape, but the power of ice as an erosive force has created our landscape. From our beautiful Corrie lakes in our upland regions, our U-shaped valleys like here in Glendalough, our drumlin belts, those little orange circles, the beautiful drumlin belts that point in the direction of the ice sheets as they're advancing, and our eskers. And it's the eskers that I wanted to focus on in the Midlands of Ireland and the sites that we're interested in as part of this Just Transition study. So anyone in the Midlands of Ireland is familiar with the landscape of these snakes winding their way across the landscape. And they've been hugely important in terms of human habitation of the planet of Ireland since the earliest hunter-gatherers. So they form at the end of an ice age. So if you imagine the Antarctic now, there's vast quantities, the Arctic or the Antarctic now, there's vast quantities of water being released back into the sea. But when an ice sheet is on top of land, as that ice sheet melts, the tunnels form at the base of the ice sheets and huge quantities of water flow through them. And with that water is sediment. Sediment gathers along the landscape. And rather than digging a river valley like you'd expect huge torrents of water to do, because they are contained and held by the ice sheets, they don't do that. In fact, they deposit material underneath them. And when the ice sheet finally disappears, what you end up with is an inverted riverbed. So this is a person here for scale, and you can see the scale of these things, and you can imagine the vast quantities of water flushing through this and bringing sediment with it and depositing it underneath. And they look just like riverbeds. They have all the characteristics of riverbeds. This is a map of the Midlands of Ireland. There's Lough Ree up to the north. The dark green lines are rivers. The shading is based on topography, so the highest ground is this ground here. But the red lines are the mapped eskers. And you can see there's eskers going everywhere, and they're really, really important part of our landscape. And the reason there are so many eskers in this area is because in the last ice age, there wasn't just one ice sheet covering the country. There were a series of domes. And the northern dome and the central dome collide in the Midlands of Ireland. And it's the interaction of those two ice sheets as they're melting that creates this incredible pattern of river network flowing underneath the ice sheets. And they're beautifully preserved in places today. One of my favorite places to walk is Knockbarron Woods. Actually, this time of year is beautiful because the bluebells are out. But you can walk along these, and when you stand on them, you get a sense of their scale, and you can imagine the force of the water and the height of the glacier above this that manages to produce this amount of material. Another feature that's quite common in the low-lying areas of the Midlands of Ireland, and people sometimes mistake these stones sitting in the middle of fields as glacial erratics. And it's understandable. Glacial erratics are huge boulders that are carried vast distances by ice sheets and deposited somewhere where you wouldn't expect them. But these aren't glacial erratics. In fact, they're attached to bedrock. So if you dig down and dug all the way around this, underneath here is the limestone bedrock, and it's sitting on top, and they're unusual shaped stones. And they're relatively common. I'm going to show you a modern one from the Andes, and it explains what they are. So this is in a lake. You've got a large rock here that's connected to bedrock, but it's been worn away here at the level of the lake. So as the lake rises and falls, just due to grain water flowing into it, it laps against it and wears out grooves. So they're called mushroom stones. And when you look at these ones, you can see the level of the water. So what these are is indicators of lakes. And if you think about the entire country of Ireland having a kilometre or so thickness of ice on it, and all that ice starting to melt, it's not going to make its way to the sea immediately. It's going to settle on the land. And we have beautiful interconnected lakes. Along the River Shannon, there are many lakes. But at the end of the Ice Age, there were far more lakes, and the lakes were much larger. We essentially had this interconnected system of lakes throughout the Midlands of Ireland. And those mushroom stones are indicators of where their ice was. But they're not the only indicator. The most important indicator are the bogs. And bogs are a hugely important aspect of the Irish landscape, in particular the Midlands landscape. And they formed as a result of these lakes. Because when these lakes came about originally, they were fed both by rainwater from above and from groundwater through the calcium-rich soils of the limestone. Very, very nutritious place. And they became anaerobic. Anaerobic means lacking in oxygen. They became anaerobic because the initial inhabitants, shelly inhabitants of those lakes, as they died, they fell to the bottom of the lake and they formed a marl layer, this white layer here. And that sealed off the lake from groundwater, and that changed the conditions in the lake. And that meant that the organic remains, plants and animals and whatever was in the lake, when it died, when it fell to the bottom, because it was anaerobic, they didn't decay, and they sat there and they built up over time. Eventually, this layer rises towards the surface of the lake, and the lake gets completely engulfed in plant material predominantly that isn't decaying, and that lake becomes a fen. Now, it looks like it's solid in the middle picture there where it says fen, and it does manage to contain, trees can grow on it, plants can grow on it, but it's actually 98% water or so. It's really, really densely, it's like a huge sponge. And as the peat decays and it becomes more anaerobic and more acidic, eventually mosses like sphagnum mosses start to dominate, and they grow inwards and they kill the trees that were growing on top of the fen, and they change the chemistry of the bog altogether, and they form a raised bog. So that's the process. They've been growing since about 10,000 years ago, so a couple of thousand years after the last ice age is retreated, and they grew at a rate of a metre or so every 1,000 years. And if you think about Ireland's been inhabited for at least 12,500 years, the last 10,000 years of human habitation of Ireland is recorded in the bogs, because they grew. When the first inhabitants came into the landscape, they were lakes, but eventually the bogs grew, and it's preserved in that bog. And of course, it's what fueled our country after we got independence. We'd no trees, we'd very little coal, and it's what gave us our power and gave us our heat, in a process that's coming to an end. That's hence the just transitions. But as this is Galaros Bog, just outside of Birr, and you can see the trees that grew on top of the fen that died, that are beautifully preserved. And then you see at the bottom of the bog where it's been cut out, you see this marl layer, this white marl layer. So that's the end of our geology talk. I hope you enjoyed it, and we hope to see you next time.